Welcome to the video where I'll be explaining one of the basic concept of analog electronic circuits. Voltage divider bias, as we all know, is universally used biasing technique. Basically, this biasing is built using a CE configuration where emitter is kept common between input and output side of the circuit. We can analyze this in two ways. The circuit at this point of time looks little complicated with few resistors, capacitors in place. However, we can simplify the circuit, do a proper analysis to get a efficient equations. That method is called exact method. It is called an exact method of analysis, which we have already done in the previous videos. Here in this particular video, let us concentrate on the easiest way of analyzing the circuit, that is using the approximate method for the analysis. So what am I doing is I am taking a circuit here. Okay, I will draw a DC equivalent for the circuit. So what will be the DC equivalent? I am removing the AC components from the circuit, which more prominently, as we see, is basically V in and V out. We are going to remove this. Once I remove V in and V out, the coupling capacitors do not hold much of the importance because they are not, the capacitors are used to block DC, pass AC. Now we do not have AC at all, so blocking DC, passing AC has no meaning. So I will rewrite the circuit this way. Sorry about the rough sketching. Okay, so this will be my VCC. This is resistor R1. This is resistor R2. Same this as it is RC, RE, and this is the emitter part of the transistor. This is the DC equivalent circuit. Now, for an approximate analysis, I am rewriting a circuit in the approximate manner by making few assumptions. What are those assumptions? First of all, we have the resistance RE. We have a resistance RE. I am making an approximate of the input resistor. I'll call it as RI, input impedance, okay, which is trying to relate the resistance RE and the transistor's current gain beta. So what will I write? I am making an assumption that RE in the circuit is nothing but 1 plus beta times of RE in the base circuit. Why? We know the relationship between IB and IE. So directly I am relating RE and input. So what am I doing? Depending on IB and IE relationship, I am trying to rewrite the equation for resistors as well. Now directly not possible, since it is an approximate method, we are doing it that way. What am I doing? Input resistance Ri is equal to 1 plus beta, correct? Current equation into Re. I am going to replace the circuit, input side of the circuit, using this term Ri. So what it will be? I have my DC voltage. I have resistance through which my input current flows into base. Suppose this is my base terminal. Okay, so from there I am writing R2 resistance, and I am bringing in my resistance which I just now assumed, that is Ri. So this is Ri resistance, This is R1 resistance. This is R2 resistance. This is applied voltage VCC. Because of this applied voltage VCC, there are current coming out. What are those current? So from VCC, I am drawing a current called as say I1. So this current reaches the point here. Okay, it bifurcates into two paths. One is IB. The other current which flows through R2 resistance, I am going to call it as I2 resistance. I am assuming my base here and the ground, that I am calling it as a neutral terminal here. This is the input equivalent, approximate equivalent. Let me make it clear. It is an approximate equivalent of the input part of the circuit. Now trying to relate the currents. As usual, I am applying a KCL here. After applying a KCL here, I will be getting what? I1 is equal to I2 plus IB. Correct? So I am getting I2 plus IB. And we already know Ri is equal to 1 plus beta times of Re. Suppose I am assuming beta is much greater than 1. So 1 plus beta will not make much difference. So I can write approximately Ri is equal to beta times of Re plus 1. I am just omitting it there. So if I am taking this relationship, I can write the equation for IB and I2. Correct? Ohm's law. Let me go to the fresh page. IB is equal to VB by its resistance. What is that resistance? Ri. And I2 is equal to what? VB divided by the resistance in the path, that is R2. Correct? Now second assumption I am making. What is that second assumption? Let Ri is equal to beta times of Re. Correct? So this value should be greater than 10 times of R2. With this assumption, we are going to assume current. If Ri and R2 relationship is 1:10, then IB will be less than 0.1 of I2. Correct? Current and the resistance relationship. From this, what can we see? I1 is equal to correct? I2 nearly equal to, I can say it is nearly equal to I2 value. Okay, so with this assumption, I have derived the relationship between the different currents in the path, that is I1, I2, and we also know the IB equation. Now let us go to the analysis at the voltage level. That is, we will be using the KVL equations as usual. Applying KVL to the circuit. Let's go to the circuit and see. VCC I1 R1 plus I2 R2. Correct? Loop. See the loop here. VCC I1 R1 I2 R2 is equal to 0. Correct? So current, if I assume is equal, then I can keep the current constant. How are we assuming the current equal? Here we have written. Correct. So let me write a KVL for it. VCC is equal to current I1 R1 plus I2 R2. We know the currents are equal. So I am taking I2 common, or you can take I1 also common, not an issue. R1 plus R2. So I am just rearranging for I2. I2 is VCC divided by R1 plus R2. Correct? So what is VB? It is again a parallel voltage. So VB is equal to I2 R2. Substitute. So I'll be getting Ri into Ib. So writing the final equation for Vb, I'll be having VCC by R2, VCC into R2 divided by R1 plus R2 there. Again we can derive a different node voltages, correct? So we can derive a similar way. VE can be derived and VC can also be derived. These are called terminal voltages. So currents we have seen, terminal voltages we have seen. So what is left? We have to derive the output voltage. So I'll take back the original circuit. So I'll be applying the KVL to the output loop. So nothing much to do with the output loop there. So it is a simple loop. We can apply the KVL directly, whether it is an approximate method or the exact method. So applied voltage is VCC is equal So see here, VCC minus ICRC minus VCE minus IERE is equal to 0 from this loop. So I am writing the same here. VCC minus ICRC minus VCE minus IERE is equal to 0. Since I want an output voltage, I can write VCC is equal to, VCE output voltage is equal to VCC minus ICRC minus IERE. We know the current VC and V are equal, correct? VC and IC are equal. So I am writing VCC minus any current. So I am taking output current only, RC plus RE. This is the derivation for voltage divider bias or universal bias circuit using an approximate method. Easiest way, just applying KVL, KCL with one assumption made, that is assuming the input resistance Ri. With this assumption, we can simplify the entire process of analyzing the circuit. Hope this video was helpful. Please write back if you have any doubt. Thank you.